All right, let's jump right in. We are surrounded by concrete, right? It's in our bridges, our buildings, our foundations. We think of it as the very definition of solid. But what if I told you there's an invisible enemy, a chemical process that's silently eating away at it from the inside out? Today, we're going to pull back the curtain on that hidden threat. This is something that happens at a microscopic level, but its effects are absolutely massive. We're talking about something that can compromise the safety of our most critical infrastructure. So, what in the world is this powerful destructive force? The culprit is called sulfate attack. And yeah, the name sounds simple, but it's actually a really complex chemical assault that turns solid, durable concrete into a weak, crumbling mess. For our purposes today, this is the villain of the story. So here's our game plan. First, we're going to get to know our enemy and the science behind how it attacks. Then we'll look at why the old ways of fighting it were just so painfully slow. After that, we'll dive into a brilliant new solution, how it works, and what it all means for building a stronger future for all of us. Okay, so let's start by looking at the damage. This isn't just some theoretical problem you'd find in a textbook. It's a very real, very visible issue, especially once you know what you're looking for. So imagine you have sulfates, which are found naturally in soil and groundwater. When they seep into the tiny pores of concrete, they kick off this devastating chain reaction. You start to see visible damage like cracking and expansion. The surface can literally start to flake off. That's a process called spalling. And in the worst cases, the material just loses all its strength and basically disintegrates. Now, this is where it gets really interesting. What is actually going on at the microscopic level? How does all of this large-scale destruction even start? Well, it all boils down to a single chemical reaction that creates this powerful, almost unstoppable force from within. Okay, so the main reaction creates these tiny little needle-like crystals called ettringite. Now to picture what's happening, think about water freezing inside a crack in a rock. As that water turns to ice, it expands, right? And it splits the rock apart. Well, ettringite does pretty much the same thing, but with chemical crystals. They grow inside the concrete's pores and generate this immense internal pressure. And hey, don't just take my word for it. This quote from the source material really nails it. The damage comes from crystallization pressure in a confined space. Those ettringite crystals are growing, and they're trapped, so they have absolutely nowhere to go but out. They literally push the concrete apart from the inside. So knowing your enemy is one thing, but how do you actually fight it? For decades, engineers have needed ways to test new concrete formulas to see if they're resistant to the stuff. But the traditional methods had a huge, huge flaw. The basic problem really came down to scale and time. See, a sulfate attack can take years, even decades, to show up in the real world. So to test for it, labs would have to use these big blocks of concrete or mortar, and then just wait. It was incredibly slow and super complicated. And this table really shows the trade-off they were always facing. Sure, you could test actual concrete, that's the most realistic, but it could take 18 months or more to get results. Using mortar is a little faster, but still not a quick fix. And the fastest method was using pure cement paste. That's the binder without any sand or gravel. But a lot of people thought it wasn't realistic enough. So you see the dilemma, right? This left innovators stuck for years, facing this terrible choice. Do you want realistic results that take forever? Or do you want fast results that might be totally misleading? Honestly, this choice really slowed down the whole process of developing tougher, more sustainable concrete. But what if that was a false choice? What if they were looking at the problem all wrong? Researchers started to question those old assumptions, and that led to a major aha moment. The solution was just beautifully simple. Instead of seeing the small scale of the paste as a weakness, they realized it was actually the key. They decided to focus only on the cement paste, what the research calls the most reactive component of concrete. It's the place where all the bad chemical reactions actually happen. It's kind of like a chef tasting just the sauce to check the seasoning, instead of waiting to bake the entire lasagna. It's just smarter. And the benefits of this approach are just huge. First off, by testing just the paste, you isolate the core chemical reaction you care about. The small samples mean the tests are dramatically faster. Plus, it's way easier to prep these little samples for a microscope to see exactly what's going on inside. The bottom line, you get trustworthy results in a tiny fraction of the time. So armed with this whole think smaller philosophy, researchers developed some really clever new ways to test for sulfate resistance much, much more efficiently. Okay, check this out. One of the coolest new methods is the unidirectional penetration approach. It starts with this really thin 5 mm disc of paste. Then, one side gets exposed to a sulfate solution. Think of that as the wet soil, while the other side is just exposed to air. It's brilliant because it perfectly mimics how sulfates get wicked up into a real structure through capillary action. Researchers can then measure the expansion and see the damage layer by layer. And the results? They're an absolute game changer. I mean, just think about it. Traditional tests took 18 months, sometimes longer. These new methods can get you solid, reliable data in as little as 3 months. That's not just a little better, that's a 6-fold acceleration in the pace of research. Incredible. So what does a faster, smarter lab test really mean for the world outside the lab? Why should any of us care about this? Well, it turns out it matters a lot. The real-world impact is huge. This speed lets us develop and prove out new, more durable concrete mixes way faster than ever before. That directly leads to safer, longer-lasting bridges, tunnels, and buildings. It also means we can finally test all these new sustainable materials, like cements made with different clays or industrial byproducts, and we can do it quickly, making sure they're not just greener, but also tough enough to last. So by really understanding this tiny enemy inside our concrete, we've found a way to build a much stronger future. And it kind of makes you wonder, right? What other invisible science is out there, quietly holding our modern world together?